Hi everybody, welcome to lecture 18 of Electrical Engineering 331. In this lecture we will talk about inversion of Laplace transforms, and I will predict that this will be one of your favorite topics in this course. This is sort of a fun thing to do once you get the hang of it. So let's jump right in. Example 18.1 says, what is the inverse Laplace transform of x1 of s equals 2s plus 3 over s plus 1 times s plus 2? Now, what that means, just to make sure that the terminology is clear here, it means what is the function in the time domain that has this Laplace transform? And and by the way, before I go any further, let me stress that this material is covered in section 3-5 of your book, and in some cases you will see, if you read that material carefully and compare it to what's in this lecture, you will see that in some cases the book and I do things in exactly the same way, and in some cases I do things in a slightly different way. And so it would be good for you to read that section and decide which way you like better. So anyway, example 18.1 then is this Laplace transform, and what I recommend is you might say a 5-step procedure. And really the first step is almost always unnecessary, so really it's sort of a 4-step procedure. So anyway, I say the first step is to check to make sure that the form that you have isn't already in the table. And really, to be honest, I think I would say the main reason I've put that in there because that will seldom be the case, that you're going to have a Laplace transform that you want to invert and it's already in exactly the right form. But by looking at the table, what that does is it helps to get you into the mode of realizing that that's what you're doing, is you're trying to manipulate the Laplace transform that you have to get it into a form that looks like what's in the table. So if you look in tables 3-1 and 3-2 in your book, you will see that there is not a form that matches this, and so therefore we can go on to step 2. Okay, step 2 says check to make sure, and this is very important. This step 2 is something that is easy to forget, but if you forget it, it will mess up the whole problem. So I would stress that you try to really pay attention to this easy step here. Check that the degree of the numerator is strictly less than the degree of the denominator. Okay, now if you look in the book, they have a slightly different way of approaching this, but this is the way that I like to say it. Check to make sure that the degree of the numerator is strictly less than the degree of the denominator. Okay, now in this case, the degree of the numerator is 1, because we have s to the first power is the highest power of s there. And if we multiplied out the denominator, we would have an s squared in the bottom, so the degree of the denominator is 2. Therefore, the degree of the numerator is indeed less than the degree of the denominator, so we can check this step. We're ready to continue to proceed with this. Okay, now the third step, and some people call this method the method of partial fraction expansions. And the reason is because of this third step. This is sort of the key step, where what you do is you take what you have and you expand it in terms of entries, in terms of fractions that look like entries in the table. And you can see that this a over s plus 1, that resembles one of the entries in your table, as does b over s plus 2. So, and of course we're trying this because we have this s plus 1 and s plus 2 in the denominator here, so that leads us to believe that perhaps we could expand this fraction in terms of these two partial fractions. So again, this is the partial fraction expansion. Okay, now if I gave you right now, before you see any of the rest of this lecture, if I said to you, okay, 2s plus 3 over s plus 1 times s plus 2 is equal to a over s plus 1 plus b over s plus 2. Find a and b. Well, I feel sure that probably what just about all of you would do would be to find a common denominator here on the left-hand side. And so you would have s plus 1 times s plus 2 in the denominator, and then in the numerator you would have various terms that would involve a and b. And then you could equate the coefficients. Up here you would have s terms and constant terms, and these would have a and b in them, and you would equate those terms to the coefficients over here. Here you have an s term and a constant term. And so when you did this, you would get two equations and the two unknowns a and b, and you would solve for them. And this is a completely legitimate way to go with this problem. But the difficulty with it is that, let's say that maybe you had s plus 1 times s plus 2 times s plus 3 times s plus 4 times s plus 5 in the bottom. Then you would have to expand this in terms of 5 partial fractions. You would have 5 unknowns, and to solve 5 equations and 5 unknowns, that's not too pleasant. It can be very tedious. So that's why we don't use that method. Now, another thing that you could do, which is along the same lines, but it's a little faster, is you could pick some convenient values of s and substitute that value of s in on both sides. For instance, if we picked s equals 0, on the left-hand side we would get 3/2, and on the right-hand side we would get a plus b over 2. So a plus b over 2 is equal to 3/2. That's one equation in the two unknowns. Now, if we pick another value of s, we'll get another equation in the two unknowns. Then we'd have two equations and two unknowns, and we could find a and b that way. That would be a little bit faster, I think in most cases, than what I described before, finding the least common denominator here, or finding, a common denominator and then equating the numerators. I think that would be a little bit faster. One thing you have to be careful of in that technique is that you don't pick any value of s that would make the denominator go to 0, because if you do that, both sides of this equation would blow up. But still, in the end, you would still need n equations and n unknowns here, where n is the number of coefficients. And so that's still something that is usually not what you want to do. But fortunately, there is another method. And even though you have talked about partial fractions probably in your calculus class, I would bet that you've never seen this method. And it's called Heaviside's method. And the way it works is the following. Look at this expression right up here. 2s plus 3 divided by s plus 1 times s plus 2 is equal to a over s plus 1 plus b over s plus 2. Now, think of what would happen if you multiplied both sides of that equation by s plus 1. Well, if you multiply the left-hand side by s plus 1, that would just cancel out this s plus 1 in the denominator. So that's fine. But if you multiply the right-hand side by s plus 1, then the s plus 1 would cancel out this s plus 1, and you would have a, and you would also have b over s plus 2 multiplied by s plus 1. Now evaluate, after multiplying both sides by s plus 1, now evaluate at s equals negative 1. And what would happen? Well, over here you'll get some value, but on the right-hand side, remember, now we have multiplied by s plus 1. So the first term just becomes a. But when we multiply this by s plus 1, we have b times s plus 1 over s plus 2. And then when we evaluate that at s equals negative 1, the s plus 1 in the numerator becomes 0. So this term goes away, and all we're left with is a. So that's Heaviside's method. Likewise, when we want to find b, we will multiply both sides by s plus 2 and evaluate at s equals negative 2. So it's just a very clever way to isolate the terms over here on the right-hand side so that you're able to solve for one coefficient at a time rather than having n equations and n unknowns. Again, you're able to solve for one coefficient at a time rather than having to deal with all of them simultaneously. So that's a really clever way, and it's called Heaviside's method. So let's see what we have then when we do that. So again, to get a, we just multiply this by s plus 1. Since a is over s plus 1, we multiply by s plus 1 and then evaluate at s equals negative 1. Okay, so when we multiply this by s plus 1, the s plus 1 in the bottom goes away, and we're left with 2s plus 3 over s plus 2, and we evaluate that at s equals negative 1, and we will get 1. Likewise, when we want to find b, we will take this, and this time we'll multiply by s plus 2, because b is over s plus 2. So we will multiply by s plus 2 and evaluate at s equals negative 2. So what do we get in this case? Okay, we will get 2s plus 3 over s plus 1, and we evaluate that at negative 2, and we get positive 1. So sticking in 1 for a and 1 for b, then we get that x1 of s up here is simply equal to 1 over s plus 1 plus 1 over s plus 2. And if you have any doubt at all, go backwards and find the common denominator here, and you will find that this is indeed equal to 2s plus 3 over s plus 1 times s plus 2. So it's real easy to check this, and I encourage you, until you have confidence in what you're doing, I encourage you to do that, to check it, because it is really easy to go backwards and check it. So once you have your expansion worked out, now each one of these terms does match an entry in your table 3-1, and so we can conclude that x1 of t is e to the minus t plus e to the minus 2t u of t. So that's the first example of inverting a Laplace transform. Now let's look at another example. This is example 18.2. This time we want to invert something that's a little more complicated. S cubed plus 4s squared plus 8s plus 12 over s squared plus 4 times s plus 4. Okay, is this form in the table? No, so we check that. Is the degree of the numerator less than the degree of the denominator? Well, the degree of the numerator is 3. The degree of the denominator, if we multiplied this all out, would be 3. So the degree of the numerator is not strictly less than the degree of the denominator, and so we have an x there, and we cannot proceed until we take care of that. Okay. So if we multiply out the bottom, this is what x2 of s is equal to. And as you can see, the degree of the numerator and the degree of the denominator are both equal to 3. So what can we do in this case? Well, what I recommend, and this is not the way that the book does these problems, so definitely recommend that you look at what the book has, and if you like their method better, go with that. But what I like to do is something I think You may have seen this in high school. It's called synthetic substitution. And you just go ahead and divide the numerator by the denominator. Now, we see that this leading term here is s cubed, and out here we have s cubed, so we put a 1 up here, and we multiply this by 1. So we get s cubed plus 4s plus 4s squared plus 4s plus 16. And then, just as we usually do when we divide, then we will subtract this from this, and we're left with 4s minus 4. So what that means is that x2 of s is equal to this number, 1, plus the remainder, 4s minus 4, divided by s cubed plus 4s squared plus 4s plus 16, which is the same thing as s squared plus 4 times s plus 4. And notice that now that we have done that step, now this term right here does have the property that the degree of the numerator is strictly less than the degree of the denominator. So for the rest of the problem, we'll just carry along this 1. We don't have to worry about it anymore because we know that the inverse Laplace transform of that is just delta of t. So we'll just carry that along with us. And now for the rest of the example, we are going to work with this. Okay. Well, that form is not in the table, so we do have to work on it some. But fortunately now the degree of the numerator is less than the degree of the denominator, so we're ready to proceed. And we have to figure out how to expand this. And it has a little difficulty here because it has s squared plus 4 in it, in the bottom. Well, if you look at your table, you will see that for a term like that in the denominator, there are 2 entries. There's an s over s squared plus 4, which would be, or s over s squared plus omega naught squared, which is the Laplace transform of a cosine omega naught t u of t. And then there's omega naught over s squared plus omega naught squared, which is the Laplace transform of sine omega naught t u of t. So I'm going to put both of those things down here, and I'll make a the coefficient of the first one and b the coefficient of the second one. And then for the third term, we just have c over s plus 4. And let me say one other thing before we go any further. When you are proposing an expansion like this, if you're ever in doubt about whether something should be included or not, include it. Because if you include something that doesn't need to be there, that's okay. Eventually you will conclude that the coefficient is associated with that term is 0. So nothing will go wrong. You're just going to do a little bit of extra work. But if you leave out something that should be there, it messes up the whole problem. You just will never come up with the right answer. So again, when you expand, if ever in doubt, include extra things rather than possibly excluding something that you need. Okay. Well, now that I have my expansion like this, this term here is familiar to us. It's like what we had in our first example. So I'm going to find C first and then try to figure out what to do about A and B. Okay, so C is the usual procedure. You just multiply. Now remember, right now we're just concentrating on this second term up here. The 1 is just getting carried along. So for C, we take 4s minus 4 over s squared plus 4 times s plus 4. We take this term, multiply it by s plus 4, and then evaluate s equals negative 4. And when we do that, we get c is equal to negative 1. Now, if we substitute that c equals negative 1, back up into here, we have that x2 of s, which is, you know, as we've seen from the beginning. Now, oh, and let me make sure you understand. I'm talking right here. This part is not x2 of s, because x2 of s is 1 plus that. So right now we're just dealing with this second term. So we have 4s minus 4 over s squared plus 4 times s plus 4. This is just, I'm bringing down this term. We'll worry about the 1 later. Right now we're just working with this. So this is equal to, we have solved for c, but we're still looking for a and b. So it's equal to a, it's equal to these three terms here. These ones, you know, this one just represents that one, so I'm not worrying about that. We have a times s over s squared plus 4 plus b times 2 s squared plus 4 plus c over s plus 4. And we found that c is equal to -1, so that's why I have that. And by the way, if you're wondering why I have a 2 in the top here, the form in the table is omega naught over s squared plus omega naught squared. So we can see down here omega naught squared is 4, so omega naught is 2. So that's why I have a 2 there. And that's to make it match with what's in the table. Similarly, that's why I have an s here in this term, because the Laplace transform of cosine omega naught t u of t is s over s squared plus 4. Okay. So now we have this. How do we find a and b? Well, in my opinion, at this point, the easiest thing to do is just to try some values of s. Try some convenient values of s. So, and always when I'm trying convenient values of s, how can you get any more convenient than s equals 0? So that's what I'll try. And you can always try that as long as s equals 0 is not one of the the values of s that makes the denominator go to 0. Okay, so if we plug in s equals 0, the left-hand side will be minus 4 over 16. This first term will disappear. That's another nice reason to pick s equals 0, because that term goes away completely. And we're left with b times 2 over 4, or 1/2, minus 1 over 0 plus 4, so minus 1/4. Now minus 4/16 is minus 1/4. B times 1/2 is b over 2. Minus 1/4 comes down. If we now add 1/4 to each side, we get 0 is equal to b over 2. And just like that, we have found out that b is equal to 0. Stick that in back up here, and of course that means that that term will just drop out. And so now we have 4s minus 4 over s squared plus 4 times s plus 4 is equal to a times s over s squared plus 4 minus 1 over s plus 4. Now again, at this point, there's different ways that you could find a. One way would be to substitute in s equals maybe 1 on each side. In fact, that would actually, now that I look at it, that would be a lot faster than what I did, because if we had picked in, if I had tried setting s equal to 1 on both sides, notice that that value would have made the left-hand side go to 0, and so then I would have had a over a times 1 over 5 minus 1 over 5 is equal to 0, which would have told you immediately a is equal to 1. That would have been a lot faster than what I did here. So, you know, there's just different ways, and sometimes it's easy to see which way is faster, and sometimes it's not quite as easy. But anyway, what I did was, since I only had one unknown here on the right-hand side, I decided to just go ahead and get a common denominator. And so when I did that, I ended up with this expression, and now I can equate the coefficients. You notice that the denominators on the left and right are the same, so now I'll just equate coefficients of the different powers of s in the numerator. On the left, we have no s squared terms. Over here, we have s squared with a coefficient of a minus 1, so that tells us that a minus 1 must be 0, since there's no s squared term over here. And similarly, for s, we have a coefficient of 4a here, and for s, we have a coefficient of 4 here, so 4a is equal to 4. And notice that the constant terms match up. We have minus 4 and minus 4. So I have two equations concerning a here. A minus 1 is equal to 0, and 4a is equal to 4. And fortunately, both of these equations give, and they must, if we have made no mistakes, then these two equations must give us the same solution, and they do. A is equal to 1. So we can plug that in right here, and we have 4s minus 4 over s squared plus 4 times s plus 4 is equal to 1 times s over s squared plus 4 minus 1 over s plus 4. Now we finally remember, coming back up here to x2 of s, that x2 of s is equal to 1 plus that fraction that we just analyzed. So we come back down here to finish the problem. X2 of s right here is equal to 1 plus the s over s squared plus 4 minus 1 over s plus 4. And as we said a few minutes ago, now we're ready to invert this, and we know that the inverse Laplace transform of 1 is delta of t. S over s squared plus 4 is corresponds to cosine 2t u of t, and minus 1 over s plus 4 gives us minus e to the minus 4t u of t. And so that's the second example of inverting a Laplace transform. Okay, now let's look at example 18.3. What's new about this one is we have this repeated root in the bottom. And so we have to ask ourselves, well, how do we handle something like that? But let's not get ahead of ourselves. Let's go through our procedure as usual. Does this form appear in the table? No. Do the degrees work out? In other words, is the degree of the numerator strictly less than the degree of the denominator? Well, the degree of the numerator is 2. The degree of the denominator is 2 plus 1 is 3. So indeed, the degree of the numerator is strictly less than the degree of the denominator. So that checks. So now we're ready to expand. And if you look in your table, you will see that you have terms that look like 1 over s plus 4, of course. But for this s plus 3 squared, whenever you have a term like this to some power, you need to include that power and all powers lower than that. So we will have an a over s plus 3 squared plus a b over s plus 3 to the first power. If this had been s plus 3 cubed, we would have a over s plus 3 cubed plus b over s plus 3 squared plus c over s plus 3, and then plus d over s plus 4. So just remember that that's the way it will go when you have a repeated root. You need to include all the powers related to that root. Okay, so in this case, then we have 2 of them, and then the c over s plus 4. And now we want to find the coefficients using Heaviside method, if possible. Well, Heaviside method for finding a is just what you would expect. We will multiply both sides by s plus 3 squared, and then evaluate at s equals -3. And when we do that, we will get this. And when we evaluate at -3, we get a is equal to 1. Now, how do we find b? Well, if you look at the book, it says that what you should do is multiply x3 of s by s plus 3 squared, just like we did here, but then take the derivative of the resulting term, or the resulting expression, take the derivative of that expression with respect to s, and then evaluate that derivative at s equals -3. That can be sort of tedious. So what I prefer to do is just to hold off on b and to go ahead and find c first, and then we'll find b in another way. So c is just like what we've done before. So we know that we'll just multiply x3 of s by s plus 4 and evaluated s equals negative 4. And when we do that, we get c is equal to negative 1. So if we stick in a equals positive 1 and c equals negative 1 up here, we will end up with this equation right here. S squared, let me make sure you can still see it. There we go. So this is, I'm working with this equation up here, but substituting in a equals 1 and c equals negative 1. So we get s squared plus 9s plus 19 over s plus 3 quantity squared times s plus 4 is equal to positive 1 over s plus 3 squared plus b over s plus 3 minus 1 over s plus 4. Now, rather than using, and if you want to use this method to find b, that's fine. But to me, taking that derivative, this is, you're going to have to use the quotient rule because you're taking the derivative of a fraction. To me, that gets sort of ugly. What I would rather do is go again with this method of just picking a convenient value of s and see if it's easy to solve b that way. And again, always when I pick a convenient value of s, the first one I try always is 0, because 0 is not one of the values of 0 that makes the denominator go to 0, so we should be in good shape. So if we pick 0, on the left-hand side, we will have a 19 in the numerator, and in the denominator, we will have 3 squared, which is 9 times 4, 36. Okay, on the right-hand side, when we pick 0, we'll have 1 over 3 squared, so that's 1/9, plus b over 3 minus 1 over 0 plus 4 is minus 1/4. Now you can see on the right-hand side that it will be convenient. Well, the least common denominator is 36, which matches the denominator on the left-hand side. So that certainly should be the direction we'll go in. So let's 1/9 is 4/36, b over 3 is 12b over 36, and minus 1/4 is minus 9 over 36. So when we collect that all together, we have 4 plus 12b minus 9 over 36. So we have 19 over 36, that's the left-hand side, is equal to this, which is 12b minus 5 over 36. So 19 is equal to 12b minus 5. Adding 5 to each side, we get 12b is 24, or b equals 2. And so substituting that in, then x3 of s is 1 over s plus 3 squared, plus 2 over s plus 3, minus 1 over s plus 4. Each one of these terms is in your table, and so we have x3 of t is equal to t e to the minus 3t plus 2 e to the minus 3t minus e to the minus 4t, all multiplied by u of t. And now we're ready to do one last example of this method. What is the inverse Laplace transform of x1 of s, which is equal to 1 minus e to the minus 4s times 24s plus 40 over s plus 2 times s plus 10? Okay, well, again, we start, this is not in the table. Now, what about the degree? It's not so clear maybe with this e to the minus 4s, but we're going to just sort of keep that on the side and worry about the rest of this fraction. Because you already know what's going to happen with that e to the minus 4s. It's just going to cause a time shift. So that should not be any major difficulty in the end. And the degree of 1 is just 0, so that doesn't change the degree. So let's just look at the rest of this, try to get a partial fraction expansion for that, and then I think we'll be able to finish up this problem easily. So we're looking right now at 24s plus 40 over s plus 2 times s plus 10, and then we'll include that other term at the very end. So 24s plus 40 over s plus 2 times s plus 10, the degree of the numerator is indeed less than the degree of the denominator, so we can proceed. And as I said, now we're going to keep this term 1 minus e to the minus 4s to the side. So we'll have 24s plus 40 over s plus 2 times s plus 10 is equal to a over s plus 2 plus b over s plus 10. And so this is perfect for the heavy side method. A a is over s plus 2, so we'll multiply by s plus 2 and evaluate at s equals negative 2, and when we do that, we get a equals negative 1. And then for b, since b is over s plus 10, we multiply this by s plus 10 and then evaluate at s equals negative 10. And when we do that, we get b equals 25. So this tells us that 2s plus 40, just bring this down here, 2s plus 40 divided by s plus 2 times s plus 10 is equal to, a is negative 1, so negative 1 over s plus 2, and then b over s plus 10 becomes 25 over s plus 10. Now let's include that term 1 minus e to the minus 4s, and so we have x1 of s is equal to 1 minus e to the minus 4s times negative 1 over s plus 2 plus 25 over s plus 10. So now multiplying this out, we have minus 1 over s plus 2 plus 25 over s plus 10 when we multiply by 1, and then a minus e to the minus 4s times minus 1 over s plus 2 plus 25 over s plus 10. Well, when we invert this first term, that's real easy. We have a minus e to the minus 2t plus 25 e to the minus 10t u of t. But for the second term, it's going to be the same thing, but because of this e to the minus 4s, and now keep in mind, we'll bring down the negative sign, but because of this e to the minus 4s, we'll shift every term involving t to make it t minus 4. So this expression here looks just like that, but with t replaced by t minus 4, and likewise the u of t becomes u of t minus 4. And so you see that in the end, it wasn't difficult at all for us to handle that e to the minus 4s term. So I believe that all of these examples should be sufficient for you to complete test 18, and then in lecture 19 we will continue to look in still more detail or other more examples of inverting the Laplace transform. So good luck. That concludes lecture 18, and good luck.